Welcome to the class. So last class we have discussed the stress strain properties of material. So today we'll just take forward our last class and we'll discuss about the principal stress and strain. What is principal stress and principal strain? So at the initial classes we discussed the stress block and the free body diagram as well. So this is a stress block. So this is small cube we have considered. So maybe from entire big body we have taken only small portion of it. So when you make a cut, so this I'll just draw it. So maybe you have a big body. So from this body, a small portion you have taken a cut, and this cut is this one. So whenever you make a cut from a body, basically we expose the internal forces. So this body may be some external forces may be applied in this body. Some external forces may be applied. So because of these external forces, their internal forces are generated inside. So whenever I make a cut or if I take any section, basically I am exposing all the internal forces. That's how we discussed in the initial lectures, first lecture. So now this small cube, actually I cut it from this body and I enlarged it here. So as I have actually taken a section, so I have exposed all the internal forces. So each face, now if you see, each face of the cube has three forces. What are the three forces? So one is normal force. So what is normal? Which is actually normal to the plane is normal force. And these two are the shear force, which is along the plane, we call it shear force. So each plane has two of shear force, that is tau in two direction, and one is that normal force, that is sigma y. So like the total each phase, if you see, all the three forces are exposed. So this is the general state of stress. Now what is plane stress? So plane stress is if we consider only two-dimensional case, only 2D case, then we call it is a plane stress. So this one is three-dimensional, whereas this is actually two-dimensional. So each phase will have shear force, which is actually along the surface, along the plane, and the normal face is always normal to the section. So like that, if you see all the directions, you have the shear forces and the normal forces as well. So now what is principal plane and principal stress? So principal plane is where there is no shear stress, just it will be shear stress, not shear. Where there is no shear stress, only normal stress, that we call it principal plane, and that if stress is, we call it normal stress or the principal stress. So in a body, some plane must be there. So in that plane, there won't be any shear stress. So shear stress tau will be 0, whereas normal stress will have some value. So that plane actually we call it principal plane. So principal plane means where shear stress is 0. So that plane we call it principal plane. So the normal stress acting on a principal plane is called principal stress. So whatever normal force is acting in the principal plane, normal force acting in principal plane, that stress we call it normal stress. So again, I'll just repeat it. What is principal plane? So for example, you have a body and some forces are acting. Maybe this type of forces are acting. So in this body, there will be a one plane or the section. In that section, there won't be any shear stress. What is shear stress? We discussed that is stress along the section. So shear stress, we call it tau. Tau will be 0, but whereas sigma won't be 0. Sigma is your normal stress. So that plane we call it principal plane, and that stress we call it principal stress. So now how to calculate the principal plane and principal stress? We have two methods to do that. One is analytical method and another is graphical method. So in this course, I will discuss analytical method, graphical method. I will discuss, if possible, I will discuss in the next class. But in this class, I will discuss the analytical method. So the analytical method for determining the stresses on an oblique plane. So now we'll calculate how you can find it out, the stresses in an oblique section. So now consider this as a body, and tension force is acting P on this body. Now if you take a section here, EF, EF section, this horizontal, this vertical section, this EF section, then how much is the stress in this section? So stress will be P by A. So P is a force, axial force is acting, and the cross-sectional area I considered is A. A. So P by A is nothing but a stress in this section, EF. So the area is A, so force is P by A, stress. Similarly, another section I have taken now, FG. This is a section which is actually theta, it is making angle theta with EF. So now how much is the area of EF? So we know the area of EF is A. Now what is the cross-sectional area of FG? So FG equal to, we can convert because this angle is theta, so we can convert, we can write FG equal to EF by cos theta, because this angle is theta. So just so FG is basically EF by cos theta. So what is EF? So again, we have discussed EF is nothing but A, so just replace EF by A, so A by cos theta is the cross-sectional area of FG. So now how much, so what is the stress in that FG? Now here this is the stress of EF, that is vertical plane. Now what is the stress for FG? So FG stress will be force by area. So what is force? Force is P acting in this direction. So P by, what is area now? Area is A by cos theta. So earlier it was P by A was the area. Now here A is equal to, area is equal to A by cos theta. So what is force? Force is P, area is A by cos theta. You have P by A cos theta. Now P by A is your sigma. So just replace P by A with sigma, so sigma cos theta. So stresses in this plane, FG plane, will be sigma cos theta. So now let's consider Pn. What is Pn? Pn is the component of force P normal to the section PG. So now, so this P is acting horizontal. But now we are considering, we have to calculate the what is the stress in this oblique plane. So that is the oblique section. Stresses of that actually we have to calculate. So this P is actually acting horizontally, but for this plane, so this is the normal force. So normal to this plane is this direction. So this direction we call it Pn. So that is the Pn. So Pn is always P cos theta, because so this is the P and this angle is theta. This angle is theta. So this Pn is basically P cos theta. So Pn is basically P cos theta. Now similarly PT is the P is acting in this direction. Now how much force is acting along the section, that we call it PT. So PT will be P sin theta, always because theta is here. So this normal direction will be P cos theta, and the shared direction it will be, that is towards the section, it will be P sin theta. So now how much is the normal stress in this section? So normal stress in this section will be normal force is Pn by the cross sectional area. So that's what we did. Normal stress sigma is equal to what is the normal force in this section, which is Pn by the area. So area in the last slide we have calculated. A by cos theta is the cross-sectional area of this section, and this force is Pn. So Pn by A cos theta. Now Pn, again we have computed P cos theta. So just replace Pn by P cos theta, and A cos theta is still there. So once you simplify this, you will get P by A cos theta into cos theta, or P by A cos theta square. So P by A is again sigma. Last slide if you see. So sigma cos square theta. So normal stress in this section will be sigma cos square theta. Now similarly, if you want to find it out, what is the tangential stress in this oblique plane? So what is the shear force or the tangential force by the area? So tangential force is how much? Pt. Pt is basically P sine theta. So this is original P component. So its inclined component is P sine theta. So tangent force will be P sine theta by cross sectional area, P by cos theta. And then if you simplify P by A sine theta cos theta, if you replace P by A with sigma sine theta cos theta, then sigma by 2 into 2 sine theta cos theta, we can do it. And 2 sine theta's formula is basically 2 sine theta cos theta is 2 sine theta. Ultimately you will have sigma 2 sine 2 theta is the shear stress of this oblique section FG. So now can you tell me where the normal stress will be maximum? So when this value will be maximum? When this value will be maximum? So when cos theta will be maximum? So when cos theta is maximum, cos theta is equal to cos 0. Cos 0 degree is equal to 1. Cos 0 equal to 1. So when theta is 0 degree, then you will have maximum value of normal stress. That is, theta is 0 means FG is matches with EF. So when the oblique plane is now EF, then you will have the maximum normal stress, and there won't be any shear stress because shear stress equation is this one. So when theta is 0, so sin theta is 0, so you will get 0. So basically EF section, this section is basically your principal plane where shear stress is 0 and this value normal stress is maximum, that is sigma. So this plane is basically the principal plane, and in this plane whatever normal stress is there, that we call it principal stress. Now can you find it out which section shear stress will be maximum? So when theta sin theta sin 2 theta equal to 90 degree, or 2 theta equal to 90 degree, then sin 2 theta is equal to 1, so you will get maximum value. So when 2 theta is equal to 90, 2 theta is equal to, when it is 90, then you will get the maximum this value. That means theta is equal to 45 degree. So when you have the angle, this angle 45 degree, in that section you will have maximum shear stress, you will get it. So that's how the stress is calculated in an oblique plane, normal stress as well as shear stress. Okay, thank you.